Have you ever wondered how to determine the total electric influence at a point when multiple charges are scattered around? It can seem like a complex puzzle to entangle all those forces at once. To calculate the resultant electric field with superposition, you simply find the electric field produced by each individual charge at the point of interest, and then perform a vector sum of all those individual fields. This straightforward approach allows us to break down a complex problem into manageable parts. This principle works because electric fields obey the property of linearity. In a vacuum or linear medium, the presence of one charge does not affect the electric field created by another. Each charge creates its own field independently, and because electric fields are vector quantities, their combined effect at any point is simply the vector sum of the individual fields present. This concept is deeply rooted in Maxwell's equations, specifically Gauss's law for electricity, which remains valid regardless of how many charges are contributing to the total field. To apply this method, start by identifying all the point charges and the specific location where you want to find the resultant electric field. Next, for each individual charge, calculate the electric field vector it produces at that location using Coulomb's law. Remember, the electric field from a positive charge points away from it, while from a negative charge it points toward it. Then, resolve each electric field vector into its Cartesian components, such as its x component and y component. Add all the x components together to get the total x component, and do the same for the y components. Finally, recombine these total components to find the magnitude and direction of the resultant electric field vector. An important aspect to remember is that the principle of superposition simplifies what could otherwise be an intractable problem. It is fundamental not just for electric fields, but also for electric potentials and even magnetic fields. This ability to linearly combine effects is a hallmark of many foundational physics principles, underpinning how we analyze complex systems with multiple interacting components. Understanding this principle lets you predict how a test charge would behave without having to consider intricate field interactions. By systematically calculating and vectorially adding the individual electric fields from each charge, you gain a clear, accurate picture of the total electric influence at any given point. This powerful technique provides a robust framework for analyzing electric field configurations, turning what initially appears as a daunting task into a series of well-defined steps that lead directly to the solution.